Hey everybody, we're back for some more math this week, coming at you with another math lesson. This week we're going to be going over some LHospitals Rule and some optimization topics in calculus. So I wanted to show you how to do a couple examples of these. We're going to go ahead and get started here with a LHospitals Rule example. And then we'll jump into those optimization problems where I'm going to be showing you 5 super easy steps that you can follow basically to do any optimization problem. And I'll get into this a bit more later, but not every optimization problem is going to have to go through all 5 steps. You may be able to skip one of them, which probably just makes it even easier. So let's go ahead and jump on into this first example here. Like I said, we're going to start out with a LHospitals Rule example here, first of all. And then we'll get into the optimization problems after that. So let me get this pulled up here. Okay. So when you are, thinking about LHospitals Rule or learning about LHospitals Rule, obviously it's spelled a little weird. L'Hôpital is how it's pronounced. So it looks like this. Looks like LHospitals Rule, but it's pronounced L'Hôpital. But what this rule does for us or tells us is it gives us a tool that makes it easier to solve limits. So it's a little bit weird because what we're going to be doing with L'Hôpitals Rule is using derivatives to solve a limit, which seems a little bit weird because derivatives are basically defined by limits. So it's weird to kind of think about it the other way. But there's essentially what L'Hôpitals Rule tells us. And there are a couple conditions that we need to make sure that our limit meets before we can apply L'Hôpitals Rule, which I'll get into in a second. But if we are able to use L'Hôpitals Rule, what it tells us is if we have a limit as x goes to some number, it doesn't really matter what it is. It could be as x goes to 0, as x goes to infinity, as x goes to whatever. And if we have a fraction, so if the thing that we're trying to find the limit of is a fraction, where we have some numerator, some function of x on the numerator, some denominator, which is also some function of x, we can, instead of trying to evaluate this limit, we can instead evaluate some new limit, which is the derivative of the top of our fraction over the derivative of the bottom of our fraction. So please keep in mind, we're not doing the derivative of this whole fractional function. We're doing the derivative of the top over the derivative of the bottom. So we're going to treat the derivatives separately as 2 separate functions. We're not applying the quotient rule. That's something completely different. L'Hôpitals Rule is a very specific situation where when we have a fraction that is within a limit, we can instead just take the derivative of the top and the bottom separately and create a new limit out of that. And these 2 things should be equal. Now, like I said, there are conditions that need to be met before we can use L'Hôpitals Rule. But if those 2 conditions are met, then this is going to allow us to hopefully create a simpler limit. The goal is that this limit over here is easier to find than this limit, and we know that they're going to be equal. So instead of finding this harder limit, we can find the easier one. So the conditions that need to be met is there's going to be 2 of them. And whenever you're trying to apply L'Hôpitals Rule or whenever you're thinking about applying L'Hôpitals Rule, you always need to make sure that both of these conditions are met before you do it. Otherwise, you're going to get, an incorrect result. So the first of those conditions is that we need to make sure that we're getting an indeterminate form by solving this limit. So basically what that means is if you think of each of these limits separately, basically if you just take the limit as x goes to a of f of x, or if you take the limit as x goes to a of g of x, just kind of thinking of them separately, basically evaluating this limit gives us something in an indeterminate form, which means that we would get 0 over 0 or positive or negative infinity over positive or negative infinity. So as long as the top and the bottom of this fraction both go to 0, or if they both go to positive or negative infinity as x goes to a, that's the first condition. We know that we may be able to use L'Hôpitals Rule. The other condition that we need to make sure is met is that the derivative of the bottom of our function is not going to give us 0, or I'm sorry, not necessarily the derivative of the bottom of our function, but that that the derivative of the bottom of our function is not 0 near a. So it is okay actually if g prime of x equals, or I should say g prime of a, because what we're thinking about is as x approaches a. So if g prime of a is 0, that's okay. But what we need to make sure is not true is instead that g prime of x near x equals a is not 0. So the reason for that is limits really don't care what's happening at this point. At x equals a has no impact on this limit. But as x is getting really close to a, as we get in the neighborhood of a, as we get, our x gets really, really close to a, if g prime of x equals 0 in that little area, that little neighborhood, then we may run into some issues, and we shouldn't be using L'Hopital's rule. So those are the two things that you want to look out for. And maybe another way you could see this written is g prime of x does not equal 0 near x equals a. So those are basically saying the same thing. So as long as these two conditions are met, we can use L'Hopital's rule to simplify our limit. So let's look at this example here. This example I want to show you as an example of applying L'Hopital's rule. And before applying L'Hopital's rule, let's think about whether or not we actually can. So if we look at this example here, the limit as t goes to 0, I'm sorry, this is very slow. There we go. So the limit as t goes to 0 of e to the t minus 1 over t cubed. So let's make sure that these two conditions are both met. So first of all, let's think about as t goes to 0, what is the top of this fraction going to go to, and what is the bottom of this fraction going to go to? So as t gets closer and closer to 0, we're going to get basically e to a smaller and smaller number, which anything to the 0 is just 1. Since e to the t is continuous everywhere, as our t gets closer and closer to 0, e to the t is going to get closer and closer to 1. So e to the t is going to go to 1. And then if we're subtracting 1 out of that, then this whole numerator is going to go to 0. So we know that this whole numerator right here is going to get closer and closer to 0 as t goes to 0. And then on the denominator here, as t goes to 0, t cubed is also going to go to 0, right? A smaller and smaller number, a closer number to 0, cubing it is just going to make it even closer to 0. So as we get closer and closer to 0, t cubed is also going to approach 0. So we do get an indeterminate form here. So we do have this, e to this numerator going to 0, and then this denominator going to 0. So we know that the first step is met. The other thing that we need to then figure out is the if the derivative of our denominator here is also going to 0. Or, I'm sorry, not if the derivative is going to 0, but if the derivative equals 0 near this a value here, near where t equals 0. So if we check that, basically we want to make sure that t cubed does not equal 0 near t equals 0. And in fact, t cubed is only going to equal 0 exactly when t equals 0. So actually, we do know that t cubed does not equal 0 near t equals 0, only specifically at that point. So since we know both of those conditions are met, we can use LHospitals Rule to evaluate this limit. So to do that, basically we just know that this limit is going to be equal to the limit as t also goes to 0. So this is always going to remain the same. As t goes to 0 is going to be the same. Whatever your variable is approaching is going to remain the same. Then we can use the derivative of our top function over the derivative of our bottom function. Well, the derivative of this top function, e to the t, the derivative of e to the t is just e to the t. And then minus 1, the derivative of minus 1 is 0. So that's just going to go away. And then on the bottom here, we can use the power rule. So we can bring the 3 down in front, put the t, keep the t the same, and then lower the power by 1. So, oh, you know what? I'm sorry. This g prime 3t squared is actually the thing that we want to check if it equals 0 near t equals 0. I misspoke about that earlier. So it's still going to be the same though, because 3t squared is only going to equal 0 when t equals 0, but nowhere near it. So that will still be okay. So that is actually the thing that we would have wanted to have checked to make sure that we can do that. So since both those conditions are met, we do know that these two limits are equal. Now, the tough thing here is what to do next, because remember, our goal was to hopefully do this and get some sort of limit that is actually easier than what we started with. Well, the question now is, what is going to happen if we try to evaluate this limit? Is that actually going to be easier? And if we try to evaluate this limit, we're still going to run into a similar situation, but definitely one that's a little bit different. Because at first glance, it does look like we're going to run into the same issue, right? Because this, if we look at our bottom of our fraction here, as t goes to 0, 3t squared is going to get closer and closer to 0, because 3t squared is a continuous function. It's a polynomial. It's continuous everywhere. So what that means is to evaluate, what happens to this 3t squared as t goes to 0, we could basically just plug 0 in for t. So again, it looks like what we're about to do is we're going to get some sort of fraction where we're dividing by 0, which, first glance, what you may think is maybe we could just apply L'Hopital's rule again. But think about what happens here on the numerator. As t goes to 0, e to the t actually goes to 1. So we have a little bit of a problem here, because we can't just apply L'Hopital's rule again, because this first condition is not met. We don't get an indeterminate form. We don't get 0 over 0. We get 1 over 0, which 1 over 0 is not a number. You can't divide by 0. So, we're not going to be able to just say that this limit is just 1 over 0. So we're going to have to think a little bit differently about how we could evaluate this limit at this point. And what frequently happens when your numerator is going to some value and when your denominator is going towards 0 is what may end up happening in that case, or what frequently would happen, is that your left-sided and right-sided limit, you want to kind of consider those separately. And they may be approaching the same thing, and they may be approaching something different. And that'll basically kind of tell you what to do. But what we want to do is, since we know we can't use L'Hopital's rule anymore, I'm just going to get rid of this stuff down here. First of all. Let's see what the best way to do that is. Okay, there we go. So what we are going to want to do is think about the limit as t goes to 0 from the left of this function, and the limit as t goes to 0 from the right of this function. If two one-sided limits are equal, if they both are the same and you can find both of them, they both exist and they're both equal, then we know that this two-sided limit would be equal to these each of these one-sided limits. If each of these one-sided limits is different, if they're not equal to each other, or if one of them does not exist, then this two-sided limit is not going to exist. And if this two-sided limit doesn't exist, then that's basically going to mean that the one we started with doesn't exist either. So to find each of these one-sided limits, what we can do is think about the fact that, it really does help in this case that each of the numerator and the denominator of this limit, they're both continuous functions, right? E to the t by itself is continuous. 3t squared by itself is continuous. So as we think about what the numerator and the denominator of this fraction are going to, we're going to be able to kind of gather some information based on that. So let me elaborate on that. What I'm basically trying to get at here is we want to think about as t gets closer and closer to 0 from the left. So we know that t is a negative number and it's getting closer and closer to 0. As t gets closer and closer to 0, this e to the t is going to go to the number 1. So if you think about what the function e to the t looks like on a graph, it looks something like this. At t equals 0, so right on this axis here, this is 1. Well, as we approach from the left, you can see that we're going to be getting closer and closer to 1. We're going to have a number that is a tiny bit smaller than 1, but it's still clearly a positive number all the way along here. And it is very, very close to 1 as t gets very, very close to 0. Then on our denominator here, similarly, let's think about what a graph of 3t squared looks like. It's going to look something like this. We got a parabola with the vertex at the origin, and it goes up to the left and to the right from there. So as t approaches 0 from the left, so as we kind of imagine traveling down our function, imagine like traveling down our function here from the left, as we get closer and closer to t equals 0, which is right here, again at the axis, our y value of our function is getting also closer and closer to 0. So this denominator also is getting closer and closer to 0. So basically, if our numerator is getting closer and closer to a constant positive number, and our denominator is getting closer and closer to 0, what that means is the fraction as a whole, this entire fraction that we get from doing this e to the t divided by this number that's getting closer and closer to 0, is going to approach positive infinity. Because if our denominator gets closer and closer to 0, we're dividing by a smaller and smaller and smaller number, the fraction as a whole is going to get bigger and bigger and bigger. Since we know our numerator is positive, it's going to go to a bigger and bigger and bigger positive number, which is infinity. Okay, same kind of thing is going to happen down here. So again, as t approaches 0 from the positive side, so as we come from the right now over here, imagine kind of walking down our function, and as we get closer and closer to t equals 0, we're going to get closer and closer to an output of 1. And then same exact thing over here. As our t gets closer and closer to 0 from the right, from positive t values, the output of our function gets closer and closer to 0. So again, we're in the exact same situation down here. So again, this fraction as a whole is going to go to infinity. So basically what this tells us is both of these two-sided limits go to infinity. Or both of these one-sided limits go to infinity. So as a result, the two-sided limit is going to be equal to infinity also. And therefore, by L'Hopital's rule, this original limit we started with is also equal to infinity. So I don't know if I mentioned it at the beginning of the live stream, but if you do have any questions along the way, feel free to drop those questions in the live chat. And I'll, be sure to answer as many questions as I can as we go through these. Even if you have questions that are not related to the problem I'm doing, go ahead and drop them in the comments, and I'll do my best to answer any questions we get. And one other, quick thing I want to mention about L'Hopital's rule here. This is actually one of the topics on my free Calculus 1 study guide. If you want to go grab that, there is a link down in the description that'll take you to where you can download that yourself and get it pulled up. It's a free PDF if you just put in your email. I'll email that to you. You can get it pulled up and have that pulled up as we go through these other problems as well. But let's go ahead and jump on into the optimization problems. So like I said at the beginning of this video, when you are doing an optimization problem, there's really just 5 basic steps that you want to follow every single time. And like I also mentioned, the second step can sometimes be skipped depending on what the problem is and what information you have. So let's go ahead and use this as an example to go over how to solve optimization problems. So really, an optimization problem is one where you're just given some sort of situation, whether it's like a geometric shape and how that has to be built, with certain restrictions of perimeter or area or something like that. Or if you're given, in this case, we have these 2 numbers, which we need to find. So we need to find 2 numbers whose product is 100 and whose sum is a minimum. So there's always going to be some sort of situation or some sort of relationship between numbers or side lengths of a geometric shape or something like that, where we are trying to minimize or maximize. So that's what makes them optimization problems, is we're trying to optimize how we're able to create a shape or path, through a river or something like that, or a combination of 2 numbers that has the maximum or minimum of a certain condition. So in this case, we want to minimize the sum. We're trying to make sure the sum of these 2 numbers that we're trying to find is a minimum. So let's talk about the steps that we kind of want to go through. First thing we want to do is just read the problem, and this seems a little obvious, but trust me, it is important to take a step back and actively think about this stuff before you just jump into the problem, because if not, you may get lost. It's definitely easy to get lost if you don't think about kind of where you're going. So the first thing we want to do is just read the problem and make sure we understand what it's saying and figure out what we're actually looking for and what information we are actually given. So let's think about what the question's asking us. We're trying to find 2 numbers. So right off the bat, we know our objective here is to find 2 numbers, right? We have some information about their product. We know their product is 100. And we have some information about what we're trying to achieve with these 2 numbers. We're trying to make sure their sum is a minimum. So those are kind of 3 main things right off the bat that we know the question is giving us and asking us to figure something out about. So let's kind of think about what this means mathematically and actually kind of writing out what we're looking for and what we have. So we know we're looking for 2 numbers. So it doesn't really matter what you want to call those numbers. Let's just say we're looking for 2 numbers, X and Y. Okay. We know their product needs to be 100 and that their sum is going to be minimized. So those are kind of the 2 things we want to keep in the back of our head as we go on to the next steps here. Okay, so I do have kind of written down here the steps we want to go through. So we understand the problem. We have an idea of what we know and what we're trying to find. The next thing you typically would want to do is draw a picture of the situation. Now, this is the step that a lot of times you can skip, because this is going to be applicable when you're given some sort of a description of some physical thing that's going on or some geometric shape that you can draw. In this case, we just know that we have 2 numbers. So really writing X and Y as the 2 numbers is pretty much all we can really do. There isn't really going to be any sort of picture we could draw with this. So the next thing that we want to think about, the third step, is going to be to write out our equations. Now, there's always going to be, I shouldn't say always, there's generally going to be 2 equations that we want to figure out. First of all, we need to write an equation for the thing that we're trying to optimize. So a lot of times, you can just think of this as some unknown quantity, whether it's a perimeter, a product, an area of a shape, a time that you're spent traveling, whatever you're trying to optimize. So in this case, the thing that we're trying to optimize is the sum. We're trying to make sure the sum of these 2 numbers is a minimum. Whatever you need to make a maximum or a minimum is going to be what you want to optimize. So let's just call this quantity Q. And this is the thing that we want to optimize. Well, how do we write the sum of these 2 numbers? Well, the sum of 2 numbers literally just means the first number plus the second number. So really, this quantity, this thing that we're trying to optimize or minimize in this case, is just x plus y, our two numbers being added together. So that's our first equation. The second equation we need to figure out is what is our restriction. And it is possible, there could be more than one restriction acting on this situation. In this case, really the only other information we're given is that their product is 100. So we know that the product of x and y, x times y, the product of these two numbers, has to be 100. Right? So we just use this piece of information that we're given to create our restriction equation. So that's it. These are our two equations. That's it really for the third step, in fact. So then what we need to do in our fourth step is going to be, it's kind of a two-part step. First, what we want to do is we're going to take our restriction equation. So just this equation here that just relates x and y to some number. It is the thing that is restricting x and y. They have to meet this condition of multiplying to 100. And what you want to do is solve this equation for one of your variables, either x or y. In this case, it's not really going to matter which you do. In most cases, it's not going to matter. In some cases, one may be easier than the other, but you should be able to get to your answer either way. If you want to kind of think ahead and figure out which one might be easier, that certainly could help. Can't hurt. But if you really have a hard time doing that and you want to just pick one and go with it and see what happens, you should be okay. And if you're not, you can go back and solve for the other one and try that instead. Either way, you're going to want to do that. One variable or the other is what you want to solve for. It doesn't really, if you have to come back and try the other way, sometimes that happens. That's part of math. Sometimes you got to just try stuff and see if it works. And if it doesn't, come back and try something different. But in this case, I can tell you it's not going to be easier or harder to solve for x or y. So let's just go ahead and solve for y. So to get the x over to the other side of the equation, we would just divide both sides by x. The x is going to cancel there, and we're just going to get y equals 100 over x. Okay, so the second part of this fourth step, I said it's a kind of a two-parter step, is to take this y that we just solved for. So we know 100 over x is the same as y. And you're going to plug that into your optimization equation for the variable you just solved for. So since we know that q equals x plus y, and we know y equals 100 over x, we can actually say that q equals x plus 100 over x instead. So now we have this other equation, q equals x plus 100 over x. And this is kind of our new optimization equation. This is the new equation that we want to optimize. And that is exactly what the fifth step is. So the fifth step is going to be to solve or optimize this equation. So remember what we're trying to do here. We're trying to make sure the sum is a minimum. So basically we want to make sure that this sum, this q, this quantity that we came up with, is as small as possible. Well, to do that, what you want to think about is how do you figure out where a function is as small as possible? Well, it's usually going to mean that you want to find the critical numbers and test those to figure out if they're maximums or minimums. In this case, it's going to be exactly that. So we're just going to take this quantity, which we'll just say is our new function f of x, and we want to find its derivative, because this is how you find critical numbers, right? You just take the derivative and set it equal to 0. So to take this derivative, what I'm actually going to do is, instead of thinking of this as x plus 100 over x, think of it as x plus 100x to the negative 1. So 100 over x is the same as x times, or 100 times x to the negative 1. X to the negative 1 is the same as 1 over x. So instead of finding this derivative, we can actually find this one, because these two things are equal. Well, the reason why we want to do that is because we can use power rule to find this derivative. So the derivative of this first term here, x, is just 1. And then the derivative of the second term here, we're going to do the power rule. So bring our negative 1 down in front, which makes it negative 100. And then we're going to lower our power by 1. So negative 1 minus 1 is negative 2. Okay. So then, since we're trying to find the critical numbers, we set this derivative equal to 0. And now at this point, I am going to switch this back to 100 over x squared, because now that we've taken the derivative, this algebraically is going to be an easier equation to actually solve for x. So to get x all by itself now, we can minus 1 from both sides. Then we can multiply both sides by x squared, because it's usually a good idea when you have fractions like this to kind of think about how we can get stuff all on one level, or like all on one line. Fractions kind of make things harder to solve usually. Even though that didn't do anything really to get our x by itself, it got rid of the fraction, so it's helpful. Okay, then multiply both sides by -1. That's basically just going to cancel the negative on both sides. And then square root that, and then square root that. But do keep in mind, whenever you square root both sides of an equation like this, you always need to take the positive and negative square root. So actually we would want to do plus and minus square root of 100. So x would equal plus or minus 10. However, okay, yeah, so that, one thing you want to think about with that, a lot of times with these problems, the problem may say we need to find two positive numbers or maybe two negative numbers. In this case, it doesn't specify. It just says find two numbers whose product is 100 and whose sum is a minimum. So it seems like there's not really going to be a restriction on x being positive or negative. So we do want to consider x equals positive 10 and x equals negative 10. So what we want to do from there is keep this fact in mind right here. We know y equals 100 over x. So if we're trying to find y, because remember, we do need to find two numbers, we know that, well, first of all, x can be 10 or x can be negative 10. But we also know that y equals 100 over x. So as a result, if x equals 10, y would just be 100 over 10, which is 10. And if x were negative 10, then y would be 100 over negative 10, which is negative 10. So these are two, potential, essentially critical numbers. Really what we'd want to think about is going back to this original function here, this quantity that we're trying to minimize. If we consider these two critical numbers, x equals 10 and x equals negative 10, which of those would make this a minimum versus a maximum? Well, just quickly plugging them in, we can see that plugging in x equals negative 10 is going to give us a negative number, and plugging in x equals positive 10 is going to give us a positive number. So, without doing further testing, you definitely could do the first derivative test or second derivative test to confirm. But just to kind of speed things up here, if we were to actually confirm that, what we would confirm is that x equals negative 10 is actually a minimum, and x equals positive 10 is actually a maximum. So we don't want to use this one because that makes their sum as big as possible. And what we were trying to do was make their sum a minimum, so make it as small as possible. So we know that this is going to be the two numbers that give us a product of 100. So x times y equals 100. Because negative 10 times negative 10 gives us positive 100. And their sum is as small as possible. So their sum is going to be negative 10 plus negative 10 is negative 20. So just to recap here, here's the steps if you want to jot these down. If you want to push pause and jot these down real quick, you can pretty much use these steps really for any optimization problem. So that should help make really all of them a lot easier. Like I said, we definitely want to draw a picture here if it is something that can be physically drawn. In our case, we just wanted to kind of sort out our variables and what they meant. All right, not seeing any questions here in the chat, so we'll keep chugging along. If you guys are getting value out of this, please be sure to hit that like button down below. It's a huge help to help get this video out in front of more people, and so we can keep growing the Jake's Math Lessons community and helping more people do well in calculus. So please hit that like button. It's a huge help to me in the channel. So let's go ahead and go on to our next optimization problem here. So the example we're going to be going over here is the sum of two positive numbers is 16. What is the smallest possible value of the sum of their squares? So again, what we want to do is think about the 5 kind of main steps that we're going to go through with all these optimization problems. First of all, we want to just take a step back and think about our problem and what it's asking and what it's telling us that we already know. So first of all, it's telling us that we again have 2 positive numbers and we know that their sum is 16. So notice it's telling us right off the bat that we only want to consider positive numbers. We're looking for 2 numbers and they're going to be positive. And we want to make sure to find the smallest possible value of the sum of their squares. So again, right off the bat, we know we have 2 positive numbers. We don't know what they are, but again, we can kind of just say x and y. We know they're positive, and we know their sum is 16, and we know what we're looking for. We're going to consider the sum of their squares. So that's really all we want to kind of figure out for step 1. Step 2 normally would be to draw a picture. Again, in this case, we don't really have something that the picture can be drawn. A lot of times that's going to be describing a geometric shape. Could be a variety of other things, but there's not really anything to draw here. So we can kind of skip our second step. Then the third step to these optimization problems is going to be to write out our equations. So we're going to have the equation that we're trying to optimize. So we're going to have some quantity, which we'll call Q, which we want to either make as big as possible or as small as possible. In this case, the thing that we're trying to get as small as possible is the sum of their squares. So the sum of their squares is just saying, first of all, what are their squares? Well, the square of x is just x squared. And the square of y is just y squared. And we're trying to make their sum as small as possible. So if we take x squared plus y squared, this represents the sum of their squares. Okay, so then the other equation that we need to make sure to come up with is our restriction equation. So what sort of equation is actually restricting these x and y numbers that we are looking for? Well, we are told that the sum of them is 16. So basically we know x plus y is 16. We also know they're positive, so we can also say x is greater than 0 and y is greater than 0. That's not going to really come into play until the end. In case we get negative x's and y's, we know that we can disregard those. But these are going to be the 2 equations that we want to use. Okay, so then what we want to do is we want to take our restriction equation and we're going to solve it for either x or y. So let's just go ahead and solve for y. In this case, it's really not going to matter which one we solve for, but we can just kind of randomly pick y. So we would just minus the x over to the other side and get y equals 16 minus x. So then once we've taken our restriction equation and solved it for one of our variables, we would take this and plug it into our optimization equation for the variable we just solved for. So we know that y equals 16 minus x. We want to go back up to our optimization equation and replace the y with 16 minus x. So doing that is going to give us q equals x squared plus 16 minus x squared. So do be very careful here. In our optimization equation, we had y squared. We need to make sure to square this whole thing that y is equal to. That 16 minus x needs to be in parentheses or we're going to get the wrong thing. Okay, so now let's think about 16 minus x all squared would be the same as saying 16 minus x times 16 minus x. So then we can FOIL that out to kind of simplify things for us. So 16 times 16 is 256. So we'll get 256 minus 16x minus 16x from doing that and that, which will give us minus 32x. And then negative x times negative x gives us plus x squared. Okay, and then we can simplify this by combining our like terms. So we get 2x squared minus 32x plus 256. So this is now the function or the equation that we want to optimize. So let's go ahead and just say that this is going to be our function f of x. And this is the thing that we want to either minimize or optimize, depending on what the question's asking you to do. In this case, we want to make sure the smallest possible value, because it said right here, smallest possible value of the sum of their squares. So we're trying to make sure that this equation that we're optimizing is as small as possible. Okay, so to make sure something is as small as possible, we need to first find its critical numbers, which means to take the derivative of the function, and then we'll set it equal to 0. So we'll take this using the power rule, bring the 2 down in front. 2 times 2 is 4. Lower our power by 1, which just makes it x to the 1, which is just x. Derivative of minus 32x is just going to be minus 32. The x basically falls off. And then the derivative of a constant is 0. Okay. Then to find the critical numbers, we set this equal to 0 and solve for x. So to get the x by itself, we'll add over the 32. Then we'll divide both sides by 4. Giving us x equals 8. So in this case, there is only one critical number. Typically in these optimization problems, if you do get only one critical number, that's going to be the one you go with. It would definitely not be a bad idea to confirm that by doing either the first or second derivative test to confirm that that gives us a minimum rather than a maximum, since we are trying to make this as small as possible. But just to kind of save time here, I'll leave that up to you if you want to, confirm that just to make sure. But now we know our x, so we know one of our numbers. And in fact, this is a positive number, so we know that it meets the fact that we have to find 2 positive numbers. And now what we can do is we can go back to this equation we found here when we solved for one of our variables in terms of the other one. If we know x equals 8, we can find y by plugging x into this equation. So we get 16 minus 8, which is 8. So if x equals 8 and if y equals 8, that is going to be the equation where we know that their sum is 16, 8 plus 8 is 16, and the sum of their squares is as small as possible. If we picked any other numbers besides x equals 8 and y equals 8, that added up to 16, and then squared them and added them together, found the sum of their squares, it would be bigger than it would be with these. So that is going to be it for this problem. That's how you apply those 5 steps. All right, perfect. Yeah, looks like there is a question here. If anybody has any questions, feel free to throw them in the comments. I'll do my best to answer any questions you have real quick. Can't guarantee 100% that I'll be able to answer any question you throw at me live, but I can definitely do my best if you got something. While we wait here for just a sec for any questions, if you guys are getting some value out of this video, please be sure to hit that like button while you're here if you haven't already done that. Really appreciate that help. It definitely helps out the video and helps out my channel so I can keep doing these. All right, not sure if anybody has a question they want to throw out there. I'll give it another minute or so, but if I don't see any questions posted, we'll go ahead and wrap things up here. Those are the 3 problems I had prepared for you guys in this live stream today. If you do have a question or a request of a problem you're working on that you want some help on, I'll wait another minute or so for you to throw that out there. I want to go over word problems with optimization. Yeah, I mean, do you have an example pulled up that you could throw in the comments real quick? That I could at least kind of go over the difference of that versus the 2 problems that we just did here. Because it is still going to be the same exact process. Any word problems of optimization problems, you're going to go through those same 5-step process. you're really just kind of trying to figure out, and I can get that 5-step process here pulled up again. You really just want to kind of take a minute to figure out what the problem is asking you to find. What are they giving you? What what do we need to figure out? If it's some sort of physical situation that's being described, either a geometric shape or another common one is someone has to run along a shore and swim across a river. Find the optimal path for them to take to travel that as quickly as possible. It's really the same kind of idea. You would want to go ahead and draw a picture at that point, and then write your equations out of the equation that you're trying to optimize and the equation that is kind of restricting things. So in our examples, we knew that the sum or difference or product of our numbers that we were looking for had to equal a certain thing, which is pretty common. In geometric shapes, a lot of times it would say like, make sure that the perimeter is a certain amount, or, maybe a lot of times you're building a rectangular fence and that fence on one side is going to cost $2 per foot or something like that. And fence on another side costs $3 per foot. Again, you want to kind of figure out your equation of that restriction. So write out how your variables that you've introduced, your X and Y, have to add up to a certain amount, which is going to be your restriction equation. Then you would solve the restriction equation for one of your variables, plug that into your other optimization equation. Now you have a single variable equation that you can find the critical number and find the max or the min. And then you would just, take the derivative of that function, since it's just a single variable function at that point, take its derivative and set it equal to 0 to find the critical number. And that critical number should be the point you're looking for. Not a bad idea to confirm with the first or second derivative test, just to make sure you didn't make an mistake along the way or anything like that. And then you can plug that back in to your restriction equation to solve for the other variable. Really the same process, no matter what kind of word optimization problem or word problem optimization problem you're dealing with. All right, cool. Well, yeah, we'll go ahead and wrap things up there. That's all I got for you guys. If you haven't already hit that like button on your way out, please be sure to do that, and subscribe to my channel. Hit that bell icon so you're notified when I go live. And thanks for coming. See you next time.